Thank you. So WebCT is a web-based application which basically glues a bunch of things together. But before that, I'm going to quickly discuss about X-ray simulation. This has sort of been a major theme this year for this get-together. And last year, it was mentioned a couple of times, but not really discussed in depth as we see now. X-ray simulation is increasing the popularity towards digital twins, component testing, and with the uses of machine learning getting bigger and bigger, you need larger and larger data sets to do analysis. Simulated results are actually quite useful. You can answer feasibility questions without having to book beam time. You don't need to run a sample on your scanner to see if it's even possible to scan. And you can use it to tweak parameters to get good qualities without wasting a lot of money. Monte Carlo simulations, which are sort of the most popular approaches, but they do take quite a long time for single projections. And if you're just using Monte Carlo, you're not going to be able to generate a large enough data set to do CT reconstruction. And when you've got really data hungry machine learning methods, that is quite a large bottleneck. So in recent years, people are looking towards GPU accelerated approaches, which uses ray tracing and stuff like methods like that, rather than simulating the particles directly. But CPU is quite slow, but GPUs are really fast and can produce images very quickly. What we actually did training on Monday was using G-Virtual X-Ray, which is developed at Bangor University by Frank Vidal. And it's so fast and accurate, and provide real-time simulated X-ray rendering with no cost. It does support a wide range of languages. It has a C++ API. The most popular one, and I think it's going to be the way forward, is the Python bindings, because everyone's done data analysis knows Python is basically the world at the moment. But what that does is that makes it very easily accessible for you to mess around and do stuff with. And before I discuss a bit more about that, I sort of want to have a look at the actual digital X-ray ecosystem. So we have a collection of different spin spectral generation libraries, which people use. We have our fast X-ray simulation, and we've also got our reconstruction libraries. These reconstruction libraries all take in different data formats. They have different geometry definitions, and it can get quite messy when trying to use them all together. But thankfully, SIL exists, and we're able to wrap all of these toolboxes and libraries into one cohesive, unified API. So WebCT is a glue, which basically binds all these together, because unless you actually have programming and computer science background, learning to use all of these while you just want to see if you can scan a tungsten fiber, it can be quite complicated. So we're aiming to sort of reduce and hopefully remove the barrier of entry for people who don't focus on computer science or programming at all. So what is it? It's touted as an interactive web UI for X-ray CT real-time results. It's an easy to learn user interface, but the key point as well is that although it's easy to use, it's not too simple. All the parameters are still exposed. You can use it for proper real scans. And if you want to have a look at how specific parameters would change your setup, those are still exposed. And the best part is that it's all open source, and it's very useful tool for scan planning and training. And there's no point me standing here and chatting about it. I can just sort of show it to you. So this is sort of where my talk's going to take a bit of a difference and turn into a live demo. So this is WebCT. This is running on my browser using localhost. But because it's a server client architecture, you can host your server anywhere you want. The server right now is actually hosted on this laptop in front of you. This is not on a supercomputer or anything fast. It's just the laptop I carry around with a GPU. And so I'm going to quickly discuss the interface, and then we're actually going to go through and do our own little case study. So we are interested in the composition and makeup of nuclear pellets, and it must adhere to very strict standards for safe operation, but it's quite hard to inspect uranium because it's highly attenuating. What they normally use when they're designing and making these pellets is a surrogate material rather than messing around with radioactive powder. So they use zirconium dioxide. And it's quite popular because it acts very similar to uranium dioxide dust. But both of the pellets contain a ceramic spherical kernels, and they affect how the fuel reacts. And they want to look at detecting these kernels using non-destructive testing, which X-ray CT is excellent for. However, I personally have no experience in this material at all. I don't know what power would require. I don't know our detector parameters to get a good enough resolution. These samples are quite small, so micro CT is what we decided on using. The good thing here is that I can just use WebCT. So the user interface is quite simple. Along the left-hand side, you have different tabs. You've got your beam setup, your detector, samples, your capture plan, and then reconstruction. And this is able to provide basically straight out of a CAD tool, which outputs 3D models, and it can simulate all your projections and then perform a reconstruction for you. So we have some roughly ideas of what we want to do. We support multiple different source types, so you can WebCT, synchrotron, and medical devices. And this UI in front of you shows you your beam spectra. So the red is the unfiltered and the blue is the filtered. So if I just hide the unfiltered, this is sort of our beam spectra at the moment. This is generated with SpecPy. However, you can also switch to XspecGen by just using a dropdown and clicking update. So WebCT is focused on providing this iterative behavior. You change something, you click update, and you get your real-time changes. You don't mess around, you don't wait minutes for something to change. It's very fast. Here, I've got a copper filter on, and that's why we're getting this curve. I can remove that and then click update and see how having filters would affect my resultant beam spectra. XspecGen is supposedly more accurate than SpecPy, but it is quite a bit slower. So I'm going to swap over to SpecPy, and we can see that actually generates a different curve. I've not done any testing to see which one of these libraries is more accurate than another. So the choice is there for you to decide. Now, in our little case study, we're using a synchrotron source. So I'm going to quickly swap to a synchrotron, click update, and that's our beam spectrum. We have optional harmonics as well, which will add in these extra couple percentages up here, the first and second order. When you're scanning some specific samples, having a slightly polychromatic beam gives you more accurate results. We did touch on that during the training, and it's actually very useful. But for now, I'm just going to leave it off. So that's our beam setup. We also have our detector setup. So for the inputs, we accept millimeters because they seem to be the most useful units I've seen people use. Although we do have this sort of live updating plane here. So I type in a value and it moves. And as you can see here, I've actually chopped off the side of our little sample here. So I'm going to first use some values here because we're doing micro CT. We have a 12 by 12 and we're using 20 nanometers for the detector. So I click update, we now have the thing that our samples way too big. Talking about samples, we have a ability to add samples and change the properties as well. So this is the Dragon model. We want to remove that, and I want to add our pellet. So here's a drop-down list of all the samples here. I'm going to pick pellet and add that in. And then click update, and that's my pellet. This is made out of aluminium though, so I'm going to make a custom material. WebCT has a material library where you can define your own materials and properties. We support mixture types, elements, compounds, etc. A very useful thing is when you're creating alloys with the mixture tool. Very easy to make mixture materials. So in this case, I'm going to select our placeholder pellet, which is our zirconium, and we have our density setup. Select that. And by clicking update, I can see how that material affects my scan. I can't actually see through this. This is a linear view. So I'm going to up my energy a bit more to 150. And now I can see the beam hardening, and I know it's being penetrated. So I want to add my kernels, but my kernels aren't here. So I can just go and upload models, browse any model you want. I have an STL file here, upload, it's done. Now I can add it in. This is very useful if you have a bunch of CAD models you want to mess around with. It's quite simple. So this is a user interface, and because it's a user interface, people without any prior programming experience can use it. It's quite simple, but it's quite powerful. So I'm going to have my kernel material, which is Chromium, and then our density. So we update. So now in our little preview, it's a bit hard to see, but there are map kernels there. We can go on to taking a scan. So first off, I'm going to pitch this so we can get a flat one. And what I've actually done is that I've started generating all the projections. In this case, I am taking 360 projections across 360 degrees, but that's just a drop down away. The other very useful tool is automatic generation of the Nyquist value. So as a slider, if you want 50% Nyquist, slide up to 50%, and this is automatically calculated for you. So like I said, this is all running on my GPU. It's using GVXR as the backend to render all of these 360 projections for you. And it will pop up in a sec. There we go. Might be hard to see, but that sample is spinning. You can see the kernel's moving. If I really wanted to, I can pitch the sample a bit more and just click simulate to get rapid iteration on what your model looks like and what your projections will look like. This is way faster than Monte Carlo methods, and my laptop's it's just a laptop. What you can do if you really want, you can host the server on, say, a machine with multiple dedicated graphics cards, and your sky's the limit. And then you can use anything client and mess around with it. So say if you want to do some scan planning on an iPad, it's all web browser, you can use any form factor you want. So while that's running, I'm going to quickly discuss reconstruction techniques. Reconstruction techniques, mostly people use the standard FBP, FDK. These are all provided by SIL. But the very interesting ones I find is looking at the more iterative methods. So here they will have all their parameters expanded. You can look at the number of iterations and tolerances, and you've also got all of your regularization operators as well. The fun thing is messing around with the more complex ones, such as the reconstruction proximals. You can use an indicator box for non-negativity constraints, or you can have a mess around with something more complex like FGP, TV. And of course, the user interface is designed to be accessible, so you can always hide all the complex parameters by just clicking the little gray bar, while all the ones you'll probably commonly use are easily visible. So our sample's now a bit more interesting, and I'm going to reconstruct this. I'm just going to use FBP, click reconstruct. And this is all just using SIL methods in the background. Give it a second. So what you can do, you can increase your detector pixel size, you can change your heights and widths. If I had my horizontal sample, although you probably wouldn't have this in real life, I can arbitrarily change how high my detector is and have a region of interest. In this case, because I've reconstructed the top part, it will spin around, but my laptop's not the fastest. The long part of this as well is because all of the data is saved, because WebCT knows what it can't do. So everything here is actually exported as well. So here's a reconstruction. In the middle, we can see the sinogram. And on the reconstruction area, because we've tilted our sample, we ended up with these slices going down. And we have nice and visible kernels. So that's all in well. So if we go back to PowerPoint, we can actually look at our results. So we did a simulation using this with a flat pellet, and we've also been to diamond, and we've got our own pellet as well. And the interesting thing is that although this kernel has, this palette has multiple kernels, or actual one done at Diamond, this specific sample had one kernel. We had one sample with many more kernels, but the manufacturing wasn't good and we had cracks and streaks everywhere, which is very interesting, but we were interested in locating kernels, and that's quite a pain in the neck to do. So these values look okay, but when we're looking at our actual case study results, we can take a line profile of our simulated results here, and we did a line profile of our scan at Diamond. We actually ended up with way different values for attenuation we were expecting. We think this is due to the actual material being a powder. And the interesting parts as well, we had some structures where the powder was less dense than other parts, so we think that's due to the compaction process. This looks like a kernel, it's not actually spherical, and in a specific sample I couldn't actually find a kernel, so I don't know where that's wandered off to. And yeah, WebCT also has accessible configuration. This is a nice tool, but it's got a limit. So what you can do, you can export your configuration and load it in with the tool of your choice. We even actually support, for those who are here on Monday, GVXR configs. So you can use this tool, set up your scan geometry, and then use GVXR for rapid creation of data. Say if you have 100 samples of the same sort of shape you want to scan, you can do this for the initial setting and then write a script to run this. And of course, WebCT can just import configs. So here's a turbo prompt I'm going to import. No, it should import. And for some reason it's not. Demo woes, I suppose. That was working about just 2 minutes before I started the talk. And obviously everything has to go wrong. Interesting part as well, as a quick thing, we're actually going to work on importing other scan metadata. So if you have XTech files, we'll load in geometry for you. And as I said, come check out the development. We have a nice little link. And thank you very much.